All right, let's just jump right in. We're about to tackle one of the biggest questions in all of science, one that totally flipped our understanding of reality on its head. How are electrons actually arranged inside an atom? And as you're about to see, the answer is way stranger and frankly more beautiful than anyone at the time could have possibly imagined. It all kicks off with a really simple but kind of terrifying question. Based on everything we thought we knew about physics about a century ago, the world, well, it just shouldn't exist. Every single atom should have collapsed on itself in a blink of an eye. So, why are we still here? So, the investigation really begins with the first decent picture we had of the atom. Back in the early 20th century, a scientist named Ernest Rutherford came up with what we call the solar system model. You've probably seen it, a dense positive nucleus like the sun, and these tiny little negative electrons orbiting it like planets. It's a really nice, clean image, but it had one massive, fatal flaw. Okay, so here's the deal. We all know that opposite charges attract, right? But the physics of the time also said that any charged particle that's accelerating, and yeah, orbiting is definitely a form of acceleration, should be constantly radiating away energy. This means the electron would lose steam, its orbit would decay, and it would go into a death spiral right into the nucleus. Poof. So this is the giant contradiction that scientists were staring at. On one hand, their theories predicted total catastrophic collapse for every single atom in the universe. But on the other hand, well, you can just look around. Reality is that atoms are incredibly stable. The universe holds together just fine. Something was deeply, profoundly wrong with the old physics. So how in the world do you solve a mystery that's happening at the very heart of matter? Well, it turns out the first big clue didn't come from poking at atoms directly. No, it came from studying something completely different: light. The secret to the atom's stability was hiding in the very nature of light and energy itself. For a long, long time, scientists understood light pretty simply. It was a wave of energy, what we call electromagnetic radiation. Think of it like ripples in a pond, traveling through space, just carrying energy. The visible light we see, that's just one tiny sliver of a huge spectrum that includes everything from the radio waves that bring you music to the X-rayers at the doctor's office. And every wave has two key properties: its wavelength, which is a distance from one peak to the next, and its frequency, which is just how many peaks pass by you every second. And as you can see, they have this inverse relationship. A long, lazy wavelength means a low frequency, and a short, choppy wavelength means a really high frequency. Simple enough? But then things got weird. A bizarre experiment showed something that the simple wave theory just could not explain. Scientists found that if you shine light on a piece of metal, you can actually knock electrons right off of it. They called this the photoelectric effect. But there was a really strange catch. Here's the crazy part. Wave theory would tell you that any color of light, as long as it's bright enough, as long as the wave is big enough, should have enough energy to knock an electron loose. But that's not what happened. You could shine a super dim blue light and electrons would pop right off. But you could blast that metal with the most intensely bright red light imaginable, and nothing. The color, which really just means the frequency, was what mattered, not the brightness. Why? The first piece of this new puzzle came from a physicist named Max Planck. He came up with a really radical idea. What if energy isn't some smooth, continuous thing? What if it only comes in these little discrete packets he called quanta? It's not a ramp, it's a staircase. You can stand on one step or the next step up, but you can never, ever stand in between the steps. And then, building on Planck's staircase idea, Albert Einstein took the next huge leap. He suggested that light itself is made of these energy packets. He called them photons. This meant that light isn't just a wave, it's also a stream of particles. Each particle of light carries a specific punch of energy. This whole wave-particle duality thing was absolutely mind-blowing. And this particle idea explains the photoelectric effect perfectly. It's like one of those carnival games. Low-frequency red light is like throwing 1,000 ping-pong balls at the bottle. No matter how many you throw, none of them has enough oomph to knock it over. But high-frequency blue light, that's like throwing a single heavy baseball. That one particle, that one photon, carries enough energy in its little quantum packet to get the job done. Okay, so clue number one, energy comes in packets. Now, the second big clue came from looking at the light that atoms themselves give off. It turns out every single element has its own secret color code, like a unique fingerprint made out of light. So here's how it basically works. An atom is usually just chilling in its lowest energy level, what we call its ground state. If you zap it with some energy, like running electricity through it. An electron gets excited and jumps up to a higher energy level. But it's unstable up there. It can't stay, so it quickly falls back down. And when it does, it shoots out that extra energy as a little particle of light, a photon. This is literally what makes a neon sign glow. Now, if that electron could have just any old amount of energy, you'd expect to see a full continuous rainbow when you split that light with a prism. But that is not what we see, not even close. If you look at hydrogen gas, for instance, you only get a few super specific, sharp lines of color. It's like a unique barcode made of light, and the old physics had absolutely zero explanation for this. So this became the next great mystery. What in the world were these atomic barcodes trying to tell us? Why were atoms only allowed to spit out these very specific frequencies of light, and nothing in between? The answer to this would finally crack the whole case open. And the person who finally put it all together, the unstable solar system model, these weird light particles called photons, and those mysterious color barcodes, was a Danish physicist named Niels Bohr. He came up with a new model for the atom that was simple, it was elegant, and it was completely revolutionary. Bohr's huge idea was basically to take Planck's quantum theory and apply it directly to the atom. He said, look, electrons can't just orbit anywhere they want. Nope. They are restricted to specific, fixed energy levels. Think of it like rungs on a ladder. An electron can be on the first rung, or it can be on the second rung, but it can never float in the empty space between the rungs. And this is the brilliant solution to the barcode mystery. When an electron falls from a high-energy rung down to a lower one, it spits out one photon. And the energy of that photon, which determines its color, is precisely equal to the energy gap between those two rungs. Since only certain rungs are allowed, only certain jumps are possible, and that means only certain colors of light can ever be created. The barcode made perfect sense. So just like that, Bohr's quantum model was a huge success. It finally explained why atoms don't just collapse on themselves. There's a bottom rung, a stable ground state, and the electron just can't fall any further. And it perfectly predicted the barcode spectrum of hydrogen. This was it. This was the birth of a whole new science, quantum mechanics. But you have to understand, this wasn't just a new model for the atom. This was a brand new rule book for the universe, a completely different way of seeing reality at its most fundamental level. And the legacy of this discovery, well, it shapes pretty much everything we do today. Now, it's important to be clear. Bohr's model wasn't the final answer. It worked perfectly for hydrogen, which only has one electron. But it started to fall apart when you tried to use it on more complicated atoms. But that doesn't matter. Its core idea, that energy levels are quantized, that they come in steps, that was the crucial first step that opened the door for the complete theory of quantum mechanics we use today. So why does any of this matter to you and me? Because understanding these strange quantum rules is the reason our modern world even works. The semiconductors inside your computer and your phone, the incredible precision of a laser beam, the technology behind an MRI scan, all of it is possible because we figured out how to understand and control these quantum leaps happening inside of atoms. And that leaves us with one last kind of mind-bending thought to chew on. The solid, predictable, common-sense world we see all around us, it's all built on a foundation of particles that follow these bizarre, probabilistic rules. They only exist in specific states, and they make these instantaneous leaps between them. If that's what's happening at the tiniest scales of the universe, what does that really say about the nature of our reality?